Young Anna Wu, who's a master's student at University of Michigan, and Chad Sharp, who is a PhD student at University of Michigan, who will present zero-knowledge proofs for legacy signatures. So welcome on stage.
Hi everyone. Today we are going to talk about how to transform existing signatures into his advanced one. And the results come from two papers. One is at Oakland this year, and another one is forthcoming. Signatures is very important in ensuring the trust, authenticity in the modern system, but sometimes we want some advanced guarantees. We might want proof of possession to prove to you that we have a valid signature message pair issued by the signer without reviewing the signature or the message. These advanced signatures enable different applications, but to make these applications practical, we want fast signer, fast verifier, and small signature. One approach is to create tailor-made signatures for this purpose. So they can be very efficient, but we often have real-world constraints that make it difficult to change the legacy signer. So we want legacy compatibility. The existing solutions are slow in our setting, so we want both efficiency and legacy compatibility. And this is especially difficult for post-quantum signature. We want to maximize the legacy compatibility. With a standard signature, the user can create an advanced signatures, such as proof of possession without accessing to the secret signing key or changing the signer. Our approach is to express the policy of the advanced signatures in the CK-SNAC circuit, and we target a general constraint system like RNCS. CK-SNAC provide privacy and small proof for us, but operations like signature verifications are very expensive to be represented in the CK-SNAC circuit because these involve hashing and elliptic curve operations and so on. So we need to find a way to efficiently represent those operations in the CK-SNAC circuit. So we efficiently represent those operations in the CK-SNAC circuit, and we additionally move the expensive operations outside the CK-SNAC circuit. This led us to have a proof of possession for RSA or ECDSA with 2 kilobyte message in just 3 seconds. And the proof size is less than 0.5 kilobyte, and the verify time is less than 30 milliseconds. And our techniques can be applied to different legacy signatures. In this talk, we'll focus on how to efficiently represent the modular arithmetic and rejection sampling in the CK-SNAC circuit. And we'll also talk about how to move the expensive operations outside the CK-SNAC circuit. So the signature verifications mainly involve hashing and algebraic operations. We need to efficiently encode both in RNCS. In this talk, we'll focus on the algebraic part, specifically the modular arithmetics. Doing the modular arithmetics is difficult in the CK-SNAC because we need to use the field of RNCS, which is usually what we want to do for the modular arithmetics for. So we either need to use the right field or we emulate the modular arithmetics in the one field. And we'll do both. For the first approach, we use an existing T256 curve to create CK-SNAC with his native field the same as the base field of the P256 arithmetics. We also create a new T25519 curve for the curve 25519 base field arithmetics. And this leads to around 300 times reduction in the R1CS constraint cost. But it is incompatible with some CK-SNAC, and this only works for large prime modulus. So we need some progress on the one field modular arithmetics. So we want to emulate the modular arithmetics in the modular M road. So at a high level, we split each number into limbs to avoid overflow. Then we use some mod M operations to do arithmetics and mod P reduction. A very important subtlety here is that we need to check that each limb in input and intermediate values are in a range. And a standard method to do that is the bit decomposition, which costs 1 constraint per bit. And this contributes more than 90% of price state-of-the-art RNCS modular exponentiation. We use a new technical tool called lookup argument to largely improve the performance. And the lookup argument allows us to check the hidden values are in a public table. So we can reduce the range check program into lookup. So we create a table listing all possible values in the range. And then we check that each of the limbs is in the table. It seems that we are done because originally we need 1 constraint per bit, but now we only need 1 constraint per limbs. But to make this practical, we actually need to tackle some of the engineering and technical challenge, which I don't have time to mention here, but we get 4 to 5 times reduction in the R1CS constraint cost. So we have optimizations for modular arithmetics, but there is still algebraic operations are still expensive in CK-SNAC, such as when we want to do the elliptic curve operations. For ECDSA and add to 5519, the elliptic curve operation, like the prefix-based scalar multiplication, is especially expensive, and it costs around 80% of the cost. So we want a new techniques to offload the elliptic curve operations outside the CK-SNAC circuit. So we offload them to a Sigma protocol. But now there are 2 issues. First, we need to ensure that we need to prevent a malicious prover from providing different input to CK-SNAC and the Sigma protocol. And we also need to build a new Sigma protocol that is more efficient than we do the elliptic curve operation in the R1CS. So to tackle the first issue, we use the commit and proof variant inspired by Sigma bus. And for the second issue, we developed a new Sigma protocol for elliptic curve algebra. So now the expensive subcomponent in the CK-SNAC is replaced by just opening commitment and verifying the prover of the Sigma protocol in the CK-SNAC circuit. So now we can exchange the dynamic-based scalar multiplication in the CK-SNAC circuit for a cheap Sigma protocol outside the CK-SNAC circuit and some SNAC-friendly hashing in the CK-SNAC. So this makes us have 4 times saving in terms of the constraint cost. Now I'll pass the time to Chad.
Hi, everyone. So at first, it might seem a little bit strange to refer to any post-quantum signature as legacy because they're not in widespread use. But what we really mean by legacy post-quantum signatures are signatures that we expect future cryptographic infrastructure to be built on top of. And so to this end, we have implementations for both Falcon and dilithium. Sphinx is a future work. In general, the algebra is easier to encode for the post-quantum signatures on account of the much smaller modulus and the frequent use of linear operations like NTTs, which are more or less free in R1CS. Norm bounds have to be computed for these verifiers, but with lookup arguments, this is almost trivial. Hashing is much harder for these schemes, both because a more expensive hash function is used in the form of Ketchik, but also just more bytes need to be hashed. And finally, whereas in the pre-quantum schemes, getting a ring element out of the hash output is a simple matter of modular reduction, more complicated techniques are used in the post-quantum signatures, such as rejection sampling, or in the case of dilithium specifically, a Fisher-Yates shuffle. So for this talk, I'm going to talk about how we handle rejection sampling, which is common to both Falcon and dilithium. So to refresh, the goal of rejection sampling is given a list of values, which you can think about as coming from a hash. We want to return the first n of them that are less than some cutoff c. And it's crucial that their order remain the same. So in this example, we want to take 3 elements that are less than 25. We would select 28 and 15 in that order. And if you were going to implement this in bare metal, this would involve a lot of dynamic accesses to memory, which would be very inefficient to encode naively in a snark. So our main goal, or our main technique, is to augment the values in the original array with a Boolean that indicates whether it's above or below the cutoff, and this can be computed with efficient range checks, and also its original index in this array. And then we have the prover provide a sorted version of this array where the values are sorted first by the Boolean and ties broken by the index. Then we have to verify that what the prover gave us is actually sorted. And again, with range checks, this is just a matter of checking that the difference between adjacent elements is non-negative. And then we have to verify that what the prover gave us is a permutation of the original array. And we'd use basically a standard technique here where we encode the values as the roots of a polynomial and then do a polynomial identity test. After that, we can just take the first n elements of the sorted version, and that is our solution to rejection sampling. So for 100 16-bit values, this costs about 1,300 R1CS constraints, and considering we're doing this on the output of a very expensive hash, this effectively becomes a rounding error. So as I mentioned, hashing is really, really expensive, and dilithium is a particularly egregious example when it comes to hashing. So on screen, I have a simplified version of the dilithium verifier, and you don't have to understand like everything that's going on here. The main point is that what I've highlighted in bold are all calls to Ketchuk. And so as you can see, there's quite a lot, and we would like to move as much of this outside the circuit as possible. So let's first consider the proof of possession case. So I've highlighted public inputs in blue and private values in red. And you can see immediately that we can move this expand A call outside of the circuit because its input is public. So instead, we could just take A and T as the input to our verifier. But this is sort of all we can do, or it seems like this is all we can do, because the rest of the hashes here all take private inputs. So proof of possession is going to remain still pretty expensive for dilithium. Okay, let's switch over to the ring signature case. The ring signature case, the verifier is substantially the same, except you also check that the public key is in some public Merkle tree. And if we perform the same coloring exercise, now the public key is private and the message is public. At first blush, it seems like we're in a worse position because every hash involves at least some private input. But okay, I said the public key was a private input. It is part of the witness for the snark, but we reveal some information about it. We reveal that it's in the ring, of course. And so you could run expand A for every public key in the ring, and then just verify that the expanded public key is in the Merkle tree. So if we do that, we immediately can remove the expand A call, and then we can note this, these hashes that are used to generate mu are, the inputs are either in the Merkle tree or are public. And so we can similarly move that hashing outside of the circuit. And as long as the ring size is not very, very large, this is almost always worth it. But once we've done this, and now we can also get rid of the public key because we don't use it anymore. And now once we've done this, it seems like we're sort of at an impasse because there's this almost circular dependency in the code where C is a hash of C hat and W is some algebra in C, and C hat is then a hash of W. So it's sort of unclear if we can do any better than this or if we're stuck with these two hashes left in the circuit. And as it turns out, we can do better. And the key thing to note is that this high bits function in dilithium is very, very compressing. So for typical security parameters, Z and C are going to have about 18,000 bits of entropy. And because we're only taking a very small number of the high bits of the result, W only has about 6,000 bits. And so W is statistically close to uniformly random. And what this means is that it doesn't reveal that the high bits of AZ minus CT don't reveal anything about the public key. And so we can just publish it. And so if we publish it, this breaks the cycle that I mentioned before. Now C hat can be computed outside of the circuit, and because C hat can be computed outside of the circuit, so too can C. And what we're left with is no more SHA-3 inside the circuit. And so what we're left with is just algebra, norm check, and some snark-friendly hashing in the form of Poseidon. So this is very few constraints. In general, we suspect that the same technique would work for any kind of Schnorr-like scheme, as long as the prover's first message, which in dilithium's case is W, doesn't reveal any information about the public key. Okay, on to some results. So we can do a proof of possession for a message length 64 bytes for ECDSA and 82519, both in less than a second, with a proof size that's less than half a kilobyte. 82519 is basically always going to be a little bit more expensive for the prover because it uses SHA-512 instead of SHA-256. For our ring signatures, Falcon and dilithium, for a ring size of 64, the prover time is 1.2 and 6.2 seconds, respectively. Although this first value is entirely hashing the leaves of the Merkle tree, and it's largely due to a pretty unoptimized Poseidon implementation that we're currently using. So we expect this number to come down quite a bit. And in any case, if you're doing many verifications for the same ring, this could be amortized away. Now, so this is with pre-quantum soundness and statistical zero knowledge for the post-quantum schemes. Post-quantum soundness is a work in progress, although because we're targeting R1CS, our techniques generalize to a post-quantum snark for R1CS. So the main takeaways here are legacy-compatible advanced signature primitives are practical or nearly practical for many applications. Efficient range checks are very powerful. They really open the door for sort of non-native field operations. But hashing remains a bottleneck, at least in the cases where we can't remove it from the circuit entirely. Thanks for listening. We're happy to take questions.
Sorry, we have time for just one question.
Do you have a proof that the modification to dilithium to publish W is still secure under the same assumptions?
We have a proof sketch.
Someone can check it.
All right, let's follow up with the coffee break, but let's thank our speakers.